And so for today, we have a talk from Patrick, and Patrick is an Earth observation scientist working in the digital platform section in the Directorate of EO program at ESA. Um, he is involved in developing new and innovative applications and oversee many machine learning related activity. And he has a PhD in Earth observations. He's also overseeing the project AI-ready Earth observation training dataset that I checked CeADAR and ESA working on. So today, Patrick will do a presentation on Earth observation and machine learning, opportunity and challenge. So I hand it to you, Patrick.
Thanks, Quan. And thanks again for the invitation, for letting me speak here today and present. So you see that in the title already, opportunities come before challenges. So I think, you know, on an optimistic view here, there's a lot of opportunities and a few challenges that I want to highlight in this presentation. And I'm going to start with introducing ESA and the Directorate of Earth Observation Programs. Then take a little bit more detailed look at the Copernicus program, which is the European flagship Earth observation program. Then I will talk a little bit about the required paradigm change that has become, you know, that is materializing more and more. And then I'll talk a little bit about the use of machine learning in Earth observation and showcase some of the meaningful examples, I would say, you know, and discuss a little bit the opportunities and shortcomings there. And then I'll conclude with some, you know, optional slides that I put into the stack for informing you on funding opportunities with ESA. And I'll give you a little intro of how you could work with ESA if you have some good ideas also, okay? So let me start with giving you a little bit of detail on the European Space Agency and the Directorate of Earth Observation Programs. So ESA is an intergovernmental organization, made up of 22 member states. And the important thing to keep in mind is that all of the applications and the technology that we're working on is purely for peaceful purposes. That is part of the ESA convention when the agency was founded. So this here shows you the ESA memberships. So there's 22 member states in ESA. Ireland is one of them. And maybe also good to highlight here that ESA is not an institution of the European Union or the European Commission. It's an intergovernmental organization that's largely independent of the European Union and the European Commission. That's also why after Brexit now, the UK is still, it's going to remain a member of the European Union, of ESA. So, and then there's additional cooperation agreements with Canada and other potential new member states of ESA, such as Slovenia. Okay, just a few ideas on the budget. This is the budget for 2020. And you see here the contributions by the different countries. Usually it's France, Germany, and then with the biggest chunks of the individual member state contributions to the ESA budget. But then there's now also in the current budget, Italy is weighing in strongly. And you see the other numbers here then kind of distribute like this. And, you know, on the lower part there, you see that the budget of ESA is made up from, on the one hand, from the contributions from the member states, but then also a large chunk and an increasing chunk is coming from the European Union and EUMETSAT in part 2. This is the ESA budget for 2020 by domain. And just to highlight here that Earth observation accounts for about 23%, which is basically identical to the amount of the budget that's allocated to space transportation. The center in Italy, in Frascati, just outside of Rome, is the head of the Center for the Earth Observation Program in ESA. So we're, yes, located in the hills outside of Rome, quite nice place to visit. In the vineyards and the olive trees here. Next to Earth observation, we also have the Vega launcher program there. And it's usually a very lively place, you know, there's, you know, this start of 50,000 visitors per year, you know, so that's a lot of people that come and go in and out. And there's around 850 personnel on site usually, but yes, it's usually a very bustling place. But right now with COVID, of course, we're mostly at home. There's only 10% of staff at the moment allowed on site. So let's see how this develops further. So the ESA Earth Observation Program has this vision of, creating the golden standard for Earth observation, which we are achieving quite well. And the mission is to, taking the pulse of the planet by looking all of the different parameters that are important to, Earth science and the health of the planet, so to say. And the ESA fleet of satellites is what you see here on this slide. So there's currently 15 satellites in operation. There's over 40 in preparation. And you see here that they follow these different lines of activities. We have the science missions in this green color here, which start with ERS-1, which was the first ESA radar satellite that was launched in the 70s. And then you have the operational programs Copernicus with the European Union, and then the meteorology missions with EUMETSAT. And you kind of get an idea here on the temporal evolution. And we are here between 2020 and 2025, where you see there's quite a lot happening here. Take a closer look on that. I already said there's the science missions, so the Earth Explorers. You see that here on the left. And and then we have the operational missions here, the Copernicus mission, meteorology missions with EUMETSAT, and then the InCube program, which focuses on private-public partnerships, basically with industry. But the way these missions come into life is very different. So for the Earth Explorer missions, this works through science proposals that respond to certain calls for the next Earth Explorers. Whereas with EUMETSAT and the European Union, the planning for the missions works very differently. Right? So next to the these three fleets or these different lines of activity, ESA, of course, is also providing access to a whole range of third-party missions. And, a lot of these include very high resolution missions such as Worldview that you might be familiar with. There's also the French spot satellites or the Landsat program and so forth. So we also provide access to this data through the third-party mission agreements. And this is now taking a closer look here at the Earth Explorers, so the science missions. So these really focus on key Earth science and are really pushing the state of the art in terms of instrumentation. And not sure which one you might be aware of here, but there's GOCHI, for example, for very high precision gravity measurements, redefining the geoid, or the SWARM mission here looking at the magnetic field of the Earth, Cryosat, of course, the ice monitoring missions. And then there's two upcoming ones here too, the Biomass and Flex. And one of the newest ones that was launched in 2018 is Aeolus, which is, of course, ESA's mission looking at wind. And this is a really innovative kind of observing system using a LiDAR system, so shooting out a laser, measuring the return signal, and creating these vertical profiles of wind speed and direction of the atmosphere. And, Aeolus has been, I think there's some technical challenges that are still being addressed, but it's already being used in operational weather forecasts and making quite an impact there. This is an example here from another Earth Explorer, from SMOS, which has been in orbit for a long time. But, and this example here is a soil moisture map provided by a company in the Netherlands, by Vandesat, so which are using SMOS measurements and Sentinel-1 measurements to provide operational products here for soil moisture. Of course, with a lot of application potential for agriculture, for urban planning, for hydrology, and so forth. One slide here on the future Earth Explorer missions. So Biomass and Flex are the next ones coming up here. Biomass, a synthetic aperture radar mission in P-band. And P-band is a much longer wavelength than the current C-band missions in Sentinel-1. And P-band has a much higher sensitivity to structural parameters in vegetation and in forests specifically. And that allows you to do quite good biomass retrievals, and biomass is of course directly and closely coupled to carbon in forests. So that's the motivation here. And you see this big reflector on the satellite. So that's actually one of the first satellites that we'll see with these big reflector dishes, you know, as an antenna. And then Flex looking at the fluorescence signal, a very subtle signal that's emitted by vegetation that, you know, does photosynthesis. Okay, these were the kind of science missions, the Earth Explorers, and now we move into, you know, what is most relevant to my work, or a lot of work with commercial relevance in the land domain and so forth. That's the Copernicus program. And this is, you know, as I said, the operational program between ESA and the European Union. The ESA basically builds and operates the satellites, but they are in fact owned by the European Union, by the European Commission. And as you might be aware, you know, the Copernicus program consists of the Sentinel satellite fleets. I'm sure most of you have heard of them. So there's 6 different Sentinels. We'll take a closer look at those. So Sentinel-1 is a synthetic aperture radar system, which, you know, and these radars, they penetrate through clouds, they can image during night and day, and hence have a very high acquisition success rate, providing us a very dense stream of SAR observations, which is really unprecedented. Sentinel-2, you know, with a high number of spectral bands at 10 and 20 meter resolution, 60 meter resolution for atmospheric parameters, and also 2 platforms in orbit currently, providing a global 5-day repeat. I'll show that a little bit more in detail later. Then we have Sentinel-3, which is a global observation system, high temporal frequency, with instruments tailored for oceanic applications, and then also one for land imaging at around 300 meter spatial resolution, but daily repeat basically. Sentinel-4 will be a geostationary atmospheric mission, Sentinel-5P and Sentinel-5, so Sentinel-5P being the precursor mission for a polar orbiting satellite that provides atmospheric parameters. And Sentinel-6 was the latest launch in November of last year. Sentinel-6, codenamed Michael Freilich, providing sea surface height measurements, a very precise accuracy. So, and here the metric is that you see there in the middle. So currently, ESA, through the ESA data dissemination channels, ESA distributes 250 terabytes of data per day. Of course, there is more data that's disseminated through other channels, such as the AWS cloud or Google Cloud or the USGS infrastructure. But that's what's going through the ESA dissemination channels, and the actual related number in terms of products that are acquired per day is 25 terabytes. So 25 terabytes of new measurements are made per day. So there are certainly, you know, disciplines that acquire more data or that produce more data, but it is, you know, it is quite challenging and moving towards real big data here. So this is again looking at the Copernicus Sentinel fleet and the status. So here you see that for each of these missions, so Sentinel-1, 2, 3, for example, you have the A and B units. So that means we actually have 2 satellites flying in orbit, Sentinel-1, A and B, Sentinel-2, A and B, Sentinel-3, A and B, 2 units. And you also see that there are the C units scheduled, and then a D unit, of course. And for most of these missions, at least for Sentinel-1 and 2, and probably also for 3, we will be in a situation in 1 or 2 years where we actually have 3 units flying, which was not really foreseen because they are exceeding their planned lifetime. So, you know, this was not really foreseen, but we're probably going to have 3 units flying in orbit, which opens, you know, even more opportunities than what we have right now. Okay, so each of these are at least dual platform constellations, each of these missions. And I'll just show you what that actually means in the case of Sentinel-2. So this shows you how both units, Sentinel-2A and Sentinel-2B are flying at 180 degrees space displaced to each other in the orbit. And this is how they, you know, by orbiting the Earth from pole to pole at a certain inclination, this is how they, within 5 days, achieve a complete global coverage. And now some of you might be aware that there are, you know, commercial providers such as Planet who achieve daily coverages with the Doves. But keep in mind that the Sentinels are scientifically calibrated instruments, you know, that really work at a different precision level than Planet or other commercial systems. I'll just replay this here because it's so nice. So you see how the acquisition swath is actually 240 kilometers in width for each of those. And, you know, Earth rotates. They always acquire the imagery at the same kind of equatorial crossing time, so it makes it comparable. And that's then how after 5 days you get a complete coverage. So I'll probably talk most about Sentinel-1 and 2, because they are kind of the workhorses, if you want, for most applications. But just wanted to add one example here from Sentinel-5, which is of course also a very successful precursor mission, providing here NOT, stratospheric NO2 concentrations in Europe, and you clearly see here in this example how the industrial production belts here in Germany and in Italy come through, you know, and well, I mean, you know, the relevance is also given due to the fact that, you know, there's an estimated 70,000 premature deaths due to you know, lung sickness caused by, you know, air pollution in Europe. So there's certainly a lot of relevance for this mission too. In terms of planning of the Copernicus evolution, so we have the current Sentinels here, which include already the C&D units that will come up in the next years. But then there's the Sentinel expansion, for which there are 6 missions, I'll show you in a minute, that are right now on a track of going all into operations and implementation. And then there is the Sentinel next generation, which we are defining at this moment, which will then be relevant after 2035, when these will be launched and then replace the current Sentinels. So this is the Sentinel expansion scenario. There are 6 Copernicus high priority missions, as they are also high priority candidate missions, as they are also referred to. So there's one on CO2. There's a strong interest, of course, for that one going forward. It's also a very challenging parameter to measure from space. There's one on polar ice and snow topography. Then there's another passive microwave radiometer looking at temperature exchange. And then we have the LSTM, which is land surface temperature. And, you know, this will provide land surface temperature at a high spatial resolution, probably 30 meters at very high temporal repeat, which will be really impactful for applications in agriculture, for example. Then we have CHIME, a hyperspectral imaging component for Sentinel, and then ROSE-L and L-band SAR mission. So, and now I just want to address a little bit this paradigm change. You know, when I started with remote sensing, I don't know, around 18 years ago or so, I still had to purchase individual images for, back then, you know, it was around $600 for a single Landsat image. So that's even when I started, you know, that's what it was like. And then, you know, I think what really mandated this paradigm change in part is, of course, the open data policies that were adopted in the Copernicus program. But they were spearheaded first by the Brazilian Space Agency, making their Landsat holdings available for free. And then it was adopted by the USGS and NASA colleagues in the US, the free and open data policy for Landsat data, which was really impactful because you could suddenly use all of the acquired Landsat imagery in time series applications and for machine learning. And this was groundbreaking in terms of use and impact on applications. And so luckily this was adopted by the European Union and ESA for the Sentinel program. So the paradigm change, of course, also has become necessary due to, you know, the data volume. I mean, 25 terabytes of new products each day. We have the continuity of the program, so we know that these, you know, also I should mention probably that the Sentinel-2 is providing continuity to spot and Landsat measurements, which of course reach back into the early 1970s with measurements. So you can really create long time series here, and continuity is a key consideration for most missions, you know, as the Sentinel-1 is also providing continuity for the ESA instrument on Envisat or the ERS satellite, and the Sentinel-3 measurements are providing continuity for earlier global monitoring missions such as Spot Visitation or MODIS. Yes, and increasingly with these data volumes, of course, data sharing becomes an important aspect, and also, you know, preventing users for having to download every scene, because that, of course, becomes really complicated when you want to use all available data to create time series or generate engineer features. You know, you don't want to download this stuff. So cloud-based platforms are becoming more and more critical. Quality, ensuring the data quality for these large data volumes is, of course, a big topic. Innovation becomes, you know, much quicker and more meaningful, and you know, as do synergies between missions and the diversity of data. But all of these require the right enabling technologies and tools to enable this. You know, if we were still at the old paradigm where we had to purchase and download the data, you know, there would be a completely different picture in terms of innovation and impact, I would say, you know. Okay, so in response to these challenges, the European Union and ESA created this, the DIAS initiative, which is basically the Data Information and Access Services. And they became operational in 2018, and there are 5 different DIASes here with the URLs, which basically provide, you know, cloud-based compute infrastructures for the storage and for processing of Earth observation data and the Sentinel data specifically. Each of them have a slightly different flavor and a different focus in terms of the capabilities that are offered. But yeah, I invite you to take a look at these. So DIASes are one part of the solution. At ESA, we're trying to develop and foster this ecosystem of Earth observation platforms. And the basic idea there is that we have, you know, on the bottom half, we have the data generation layer, which is, you know, the PDGS and the infrastructures where the data is fed into the ground segment infrastructure. And at the top, we have kind of the exploitation layer, which is public institutions, commercial entities, application and science that basically use the data. And in between, you then have the resource layer that is providing, you know, a little bit of infrastructure as a service, platform as a service on top of the crude data infrastructures hosting the data. And then you have the platform services layer. You know, that's kind of the vision for the platform ecosystem in Europe. And this whole slide right now has a strong focus on Europe. Not looking here too much across the Atlantic, but you see also iCheck popping up, of course, in the resource tier layer. And for the platform services layer, that's really where we're focusing a lot of ambition now for, you know, intuitive data utilization and exploitation, you know, moving away from things like, you know, file-based thinking and file-based data access to really pixel-based exploitation of the entire archive through intuitive tools. It's kind of the mission there. And to make this all work across all of these components of the ecosystem, you know, there's a lot of work that needs to be done on the interfaces that allow these different elements and layers to communicate with each other and to define common architectures. So these are 2 additional elements that we're working on quite a bit. So I just wanted to next talk a little bit about the concept of Datacubes for Earth observation. It's also a term that is used too frequently, maybe. You know, I think whoever you ask, you know, there's different understandings of what a Datacube actually is. But from my perspective as an Earth observation scientist, you know, it is basically an arrangement that allows us to efficiently exploit the data in the temporal dimension. So basically making it much easier to align the data in a way that we can really exploit the temporal signal here, because that's where all the value is in, you know, not the single acquisition with a single measurement, but the temporal variability and the temporal signal. That is for most applications, that is true. And this figure here basically shows you the Sentinel-2 acquisition swath here again over the 270 kilometers in width horizontally. And then you see in white, the small tiles are the individual granules that the different sensors observe. And then in green and yellow, you see the different tiles that are then provided as a product and exposed as products. And in the case of Sentinel-2, it's quite fortunate because each of these tiles have a defined standard size and they have a defined standard gridding. So you can expect that each of these tiles fit well above each other, so you can align them quite easily. But with other sensor systems, that is not the case. So some images start 100 or 50 kilometers further north or so. So there's a lot of work you have to do to align the data in a way that you can get to the situation that you can do time series analysis. So, you know, one of the common problems was that people spent, you know, easily 80% of the time and effort for organizing and managing the data and, you know, organizing their in-house storage in a way that they can make these workflows run. And so these things are hopefully becoming easier and easier, and Datacubes are part of the solution. And here's a nice figure from our Australian colleagues, the way they see that here. You know, on the left you have the actually overlapping acquisitions here that, you know, geographically overlap, and then you want to bring them all into a stack so that you can really exploit the temporal signal. And to do that efficiently, that's where Datacubes come in, you know, to do all of this pixel shifting, array provisioning, and processing, so that you can really focus on the signal that's in the data. And EuroDataCube is one of the initiatives that we have, one of the capabilities that we have initiated. And it brings together a couple of different technologies. So the Sentinel Hub, then Xcube, which is a Pythonic interface to the Datacube based on X-array, and GeoDB for non-raster data, and EOX Hub, and then Jupyter Lab, of course, play a big role. And you see here on the lower part, this is all connected to the different DSs, to AWS and even the Google Cloud. And it provides you basically, you know, in the Xcube interface, a nice Pythonic way of accessing the entire data holdings without ever having to download a scene, or without ever having to do a query for file paths or file names, you know, which is still, unfortunately, the predominant way of accessing data these days. So a Pythonic way, pixel level data access to the entire data holdings. Another activity that we have initiated is OpenEO platform. And this is actually now building on top of Horizon 2020 funded activity, OpenEO, which was concluded last year. And the ambition there and the Horizon 2020 funded part was basically this scenario here, which we had 10 or 15 years ago, where there was maybe a first, you know, cloud-based data structures that allowed you to access and process some data. But all of those had their specific APIs and their specific front-end libraries, and they would then link to one specific cloud backend for accessing and processing data. And this is a problem that was addressed in OpenEO by basically defining the OpenEO API as an interface that connects all of these different backends with the different front-end libraries and the different user communities. And they did that quite well. And last year, we basically transitioned from OpenEO to the ESA funded activity, which is OpenEO platform, where we're now trying to build on top of that by creating an operational platform in a really federated environment and a federated architecture to address these remaining shortcomings in the Earth observation platform ecosystem. And really the key elements are here, you know, abstracting complexity, you know, by so that users don't have to worry about, you know, file paths and how file formats and projections and all of that, that this is abstracted from the user, that the user can really focus on exploiting and using the data. And, you know, also intuitive and simple front-end libraries that really are similar to the data science elements of the Python data ecosystem, I would say. And, you know, and also providing a clear roadmap for, you know, on the one hand, simply enabling interactive development in interactive coding environments, but also providing a clear roadmap to continental or global assessments, you know, which is not easy, of course, and where, you know, there are still some shortcomings in other environments such as Google Earth Engine or AWS. You know, it's not so easy to run a continental analysis in GE. You know, you still need to tweak it quite a bit or get in touch with the people who actually run it to do that. So I think these are a couple of the aspects that we're trying to address here. Okay, so now I'll try to talk a little bit more about Earth observation and machine learning. And for me, you know, with a background in geosciences and then a lot of scientific computing, for me, machine learning was always a tool, but I was never too much interested in the different, you know, performance of different algorithms. I was really more interested in getting the right results. And I think the feature engineering part is, in my eyes, often at least as important as the choice of the right algorithm and the right training data and the right approach. And that's what I'm going to try to highlight in the next couple of minutes. So, okay, so I already showed you the acquisition patterns of Sentinel-2 with polar orbiting satellites. And here you see a little bit of the resulting data densities that we get here in Europe. And you see there in the right chart for Sentinel-2, you see these orange areas, which are basically the overlapping orbits, you know, the acquisition swaths coming down from the poles and then overlapping as depending on the position, the latitude, basically, you know. And the same thing with Sentinel-1 there on the left-hand side. And Sentinel-1, of course, acquires data at day and night, and it can acquire data in ascending and descending orbits. That's not the case with Sentinel-2. And then, of course, Sentinel-2 as an optical multispectral system is crucially dependent on cloud-free conditions to acquire useful imagery. That is not the case with Sentinel-1 with the cloud-penetrating radar. So you see here that there are parts in Europe, in the north of Europe, you know, where you have on an annual, this is actually the number of acquisitions for July to September 2018. You have 115 acquisitions in the far north latitudes in North Norway and Sweden. But even in the Iberian Peninsula, you know, you have around 60 acquisitions for these couple of months. It's really unprecedented and groundbreaking. And even for Sentinel-2, the temporal repeat, you know, is quite good, you know. I mean, so the general metric to keep in mind here is that we get in Europe every 3 days an observation with Sentinel-2 and every 2 days with Sentinel-1. And yes, this is unprecedented, and this is really impactful for a lot of applications. And one of them is, of course, agriculture, you know, but because the agriculture, if you do analysis in agriculture, it's not the single observations that's meaningful. It's how the signal evolves over time, right? And some of you might have seen this example before, but this is an example from the monitoring for the Common Agricultural Policy subsidy payments. So farmers in Europe receive subsidies for the farmland they manage and the crops that they produce. And it's quite a complex system. And there are a lot of rules and things that need to be, requirements to be met by the farmers to be compliant for these subsidy payments. And in this example here, let me just put that on again. In this example here, we're looking at 3 different parcels here, one here, one there, and one there. And you see how the indicator here on the y-axis is basically vegetation vitality, you know, represented here by vegetation index. And you see here over the course of the growing season on the x-axis, you see how this signal evolves. And we see for these 3 fields, we see the harvesting event at about the same time here in July. Actually, 28th of July, it was a good weather day, so they all harvested their cereals here. And then afterwards, you see this gray area in the plot here, and this is actually something called a catch crop period, where the farmer grows a catch crop that kind of refertilizes the soil after the harvest. And there are some very clear rules here in the Common Agricultural Policy regarding the catch crops, that they can only stand on the field for a number of weeks. I think it's 2 or 3 weeks, after which the catch crop has to be mechanically destroyed. And you see here that 2 of these fields that we see here are compliant with this rule. They mechanically destroy the catch crop cover, whereas the last one does not. And this is just an example to show how the Sentinels are used for compliancy monitoring. And, you know, I'm not going to talk about the CAP for too long, but the Common Agricultural Policy is now moving towards a continuous, permanent, and wall-to-wall monitoring of all agriculture in Europe with the Sentinels. And this is a big shift from the previous system, where there was, you know, visual assessments and then field visits for some samples of the subsidies and everything. Anyway, this example does not have any machine learning involved. This is pure time series assessment, and that is in remote sensing and Earth observation often sufficient to do a lot of good things, you know, using the temporal signal without any machine learning. I'll show another example that's also basically just based on time series processing. This is using Sentinel-1 radar data for looking at forest disturbances and forest dynamics in Indonesia, where we have a lot of expansion of oil palm and these kind of things. And here again, you see how the acquisitions come in over the year 2017. And you see here in red, the new clearings, and you know, in this lighter red color, the established clearings. And you really see how, you know, the secondary vegetation in this case is cleared. And then you see that, you know, in many of these areas, plantations are established. So that's, you know, you see some plantation management here, but you do also see the clearing of primary forests, you know, which is, of course, has strong implications for the carbon cycle and, you know, land use policy implications and so forth. That's another example that's basically just using Earth observation time series, but there is some machine learning component involved here, I believe, for the probability operator that they're using in the background. So in terms of machine learning and Earth observation, you know, I think there was the first step change in terms of machine learning algorithms that we witnessed was kind of the point when we moved from parametric methods, such as, you know, maximum likelihood or so, to non-parametric methods. That was the first step change that already occurred 15 or 20 years ago, you know, and the typical workflow is for many applications still the same. So you see that here in the graph, you have your training reference areas, you have the corresponding image data, you know, array data, both, and then you kind of parameterize a model. You get a model, you apply a model, and you get a prediction, and you have a validation, you run an accuracy assessment, and you might have some probability outputs on top of that, right? That's, for many cases, that is the, especially for classification workflows, that is the standard workflow. And, you know, this step change in non-parametric methods was, you know, these are, you know, the ones that are really widely used are support vector classification, support vector regression. And I think random forests are really, have really shown that they are really good for generalizing these Earth observation problems. And they are also performant in terms of, you know, the time you need for training and for creating the models. And, you know, they also have a simplicity to them. They're quite conceptually intuitive. So I think both of those methods were really widely used. So, and then we have all of these new machine learning methods, the convolutional neural networks, deep learning, and so forth. And, you know, I think an observation that we are making is that in many cases, it's not really justified to employ a method there like deep learning that requires, I don't know, 60,000 CPU hours of training or GPU hours of training versus, 2 or 3 hours of training with an SVM. There's just not many good examples that really justify this. Also, many application examples like simple land cover mapping or change detection, they really do not require, they are well solvable with traditional non-parametric algorithms. So it's sometimes a little frustrating seeing all of these people trying to deploy deep learning for things that are solvable with other means. But, certainly there are some good examples, and I'll try to showcase a few of those in the following slides. But the first one that I'll show you is this one here, where we actually mapped crop types at national scale across Germany with Sentinel Landsat data. And this basically is a random forest classification using as a feature as the predictive feature the spectral time series for the different cover types and the different crop types. And here you see some examples of what the NDVI, again, a proxy for vegetation vitality, what it looks like at the single pixel level. And now you can imagine that we have this time series for each pixel over the 12 or the 9 Sentinel-2 bands that we used here. So that is the actual Earth observation data that we use to make the predictions of the cover types. And so what needs to be done here first is that you take, the 12, 14 or 15 months of data that you have, and you distill them to one meaningful measurement per 10-day interval. And then you end up with these time series, again, 9 or 10 different time series per pixel for each of these pixels involved here. And then here you see kind of how these fields change over the course of the growing season. This is a false color composite here, where these cyan colors show fields that are barren or sparsely vegetated, whereas these bright red colors are strongly vegetated conditions, and everything else is in between. And shows you how the crop phenology changes over the course of the growing season. And this is captured in the time series that we create for each pixel here. And that's what the machine learner, the random forest in this case, is using to make the predictions and the generalization of the different classes. As an example here of feature engineering for machine learning. Another example, also from my previous postdoc work here, is something we did in Brazil, where we basically reconstructed deforestation dynamics for a huge area here in Brazil, from Mato Grosso and Pará. And on the left-hand side, you see the metrics that we created. So this is all feature engineering. Huh? So there's best observation composites. There's the first and the last observation for each spectral band. There's the minimum SWIR as shortwave infrared. That is the first quartile, the median, the second quartile, the maximum SWIR observations. So you identify the maximum SWIR, but you take all 7 bands in this case, and they make up the feature set. And then we create some additional metrics here on the interquartile standard deviation, or some weighted averages of the visual and the near-infrared bands. And in this case, this worked really nicely to reconstruct the entire deforestation dynamics over 30+ years. And again, here, random forest classifier at place, but the proper feature engineering done. So another example that was very impactful was in 2013, when Matt Hansen and colleagues from University of Maryland published their first global deforestation or forest change map using Landsat data at 30 meters globally. That's a new thing. That's part of the paradigm change. So this is not easily doable. This was not feasible 20 years ago. But with the open archives and the innovation in algorithms and processing infrastructures, this has become possible. And in their case, yes, there's some machine learning that's used here, but it's a simple decision tree classifier. Very simple, even more simple than the random forest. And here again, feature engineering is the key to getting this right. So they have a very nice way of systematically engineering different time series features by looking at the year, the previous year, the average between the preceding 3 years and the succeeding 3 years, and then calculating things like the minimum, second lowest, second highest, the average between two ranges, these kind of things. And you do that by enhancing the features that you think are meaningful for the given application, right? And in the forest change case, you're looking for this contrast between a densely vegetated pixel that has a lot of shadow and low reflectance in the shortwave infrared, but high reflectance in the near infrared. And then the contrast is when the forest cover is removed, you have high reflectance in the SWIR and low reflectivity, relatively lower reflectivity in the near. So that's kind of the process that you have in the back of your head, and that you try to embed in the features that you engineer. And, University of Maryland certainly has a good approach there. Peter Potapov in charge of that. And they're also providing analysis-ready data globally now, following this recipe, so to say. Okay, thinking a little bit beyond the traditional non-parametric methods, this is, of course, a common application example these days for object detection here. This is using a convolutional neural network. This is in our race dashboard. The URL is down here. You can have a look at this. And the first example here with this is using Sentinel-2. So usually object detection uses very high resolution imagery, so sub-meter or meter resolution. We use here 10-meter Sentinel-2 data, and it works fairly well for vessel detection in harbors, for parked airplanes. We also have one that looks at flying airplanes, a community contributed indicator. So, this is certainly a commonly used application example for convolutional neural networks, that where it makes sense to work on the image patch level, whereas the traditional non-parametric machine learning algorithm work on the per pixel spectrum vector level, right, or temporal vector level. So another example, and this is one of my favorites next, is this one here from UNICEF and Development Seed, where they used deep learning technologies to map schools globally. And this is really cool because, so on this animation on the right, you see the schools that were known in this northern part of South America in red, and then you see in yellow the new schools that they mapped with this method. And what they basically use here is they take advantage of the contextual capacity and the contextual information that is contained in an image patch acquired over a school. So you see here some examples of the training data they used. And this is all using very high resolution imagery, okay? But still, in this very high resolution imagery, we see each school has like a set of large buildings. There might be a soccer field or some green space, but they all have kind of a topology that is similar, right? They're all arranged in a similar ways and then closed structure with different components. And if you represent that well in your training data, then you can pick that up in the deep learning predictions, right? And that's what they did here, very successful. So I really like this because this is also relating to one of these sustainable development goals on the right for learning and education, which 10 years ago we wouldn't have thought that remote sensing, Earth observation can make a contribution to this, but with the use of these new methods, you can actually have an impact on this kind of thing. So I really like this example. The other one that I like to showcase is here from Vito, a company in Belgium, and this is here looking at data fusion, okay? And the parameter that we have here on the top graph is the FA-par, so the fraction of active photosynthetic active radiation, the fraction of absorbed photoactive radiation. And this is derived from Sentinel-2 on the top, and the green dots here show you the actual acquisitions that we get from Sentinel-2 in Belgium in terms of cloud-free conditions over a year. Again, on the x-axis is the time. And you see, that's on the top, the Sentinel-2 acquisitions are quite sparse. There's only a few coming in. But what they then used, they used the coinciding Sentinel-1 acquisitions from the radar system. And remember, the radar is ground penetrating and it acquires ascending, descending orbits and day and night. So we get a much denser flow of observations here. You see here the different polarizations, so vertical, 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 horizontal, and the different orbits ascending and descending. We get this rich data stream, and this is always there, so we have this coinciding, this situation where the optical multispectral observations, which are sparse due to clouds, coincide with this dense stream of SAR acquisitions. And they basically have a convolutional neural network that then predicts the next APAR observation based on the SAR data stream in the Sentinel-2 feature space, so to say, predicting the next APAR observation. And you also get this, the confidence around these observations. This is a great example of the synergistic use of SAR and multispectral data and the use of new machine learning technologies. Really one of my favorite examples. And that's something where there's still quite a bit of work to be done to do this efficiently. Okay, so a few last slides here on the issue of training data. And as in so many disciplines where machine learning is used, the training data represent a bottleneck. And it's especially so in Earth observation and even the Earth observation land domain. And this here is a project that we're running with CeADAR and iCheck here. A lot of members are attending here today, I'm assuming. And that's AIREO. So AIREO stands for AI-ready Earth observation training data sets. And what we're basically trying to do is to implement to move training data in Earth observation towards FAIR data principles. FAIR is findable, accessible, interoperable, and reusable. And we're doing that by developing training data specification and best practices that make training data more reusable, more findable, and more interoperable. You find the URL here on the lower part of the slide, and then the aspect of AI ready basically relates to the fact that we want to make the training data sets also self-explanatory, so that users, that I could send the email this training data set to one of you, and you would exactly understand what you can and what you shouldn't do with it, and how it can be used and how it was created. So that's the aspect of AI ready. Yes, the landscape in terms of training data for Earth observation is relatively scarce, like in many other disciplines. There are two good sources of reference data, training data that are freely available. That's the Land Parcel Information System, which is basically the spatial data infrastructure for the Common Agricultural Policy subsidy payments. So this is freely accessible. You can experiment with it. It's a really nice data set. And then the Eurostat Lucas survey, which is every 3 years, they repeat this survey of land use, land cover, the specific grid. It's very good data. You have to filter it a lot, but it's something I encourage you to visit if you want to experiment a little bit with existing training data sets. You can do a lot with this. Okay, I have a few final slides on funding opportunities, but I realize that we're running out of time, but I'll go quickly. So there's many ways that you can work with ESA and receive funding. We're always open to good ideas, but the standard way of working with ESA is basically to look at the invitations to tender that are here in the EMIT system, where you can take a look. So that's where we announce new opportunities for tender. And then there's a couple of slides that show you how the standard procurement and tendering works with ESA. It's not a simple, complex process, but it is doable. It's competitive tendering usually, and I'll just leave these slides in here for you to revisit. Besides the standard competitive tendering, we also have the open call, which is a very nice first way for working with ESA. So here you can make a proposal. And we have 4 submission deadlines per year. And here we provide funding for 1 year of activities and up to 150,000 euros. in a relatively quick and pragmatic way. So the next submission deadline is the 26th of March, where we will evaluate the next batch of proposals, and well, you can have a contract within a couple of weeks or months, up to 150K for activities, and you define the idea. You know, there are, of course, have a look at the link. There are considerations for the evaluation, of course, that you have to take into account. There's a postdoctoral fellowship program called the Living Planet, which was just reissued. The call is open for this year for postdocs. And maybe some more information here on the EO for Society website. And there's the InCube program, which is stands for Investing in Industrial Innovation, which is kind of a co-funding scheme where ESA provides 50 to 80, I believe, % of the budget. And also here, you basically pitch the idea. So, and you know, this can range from like payload design to data science, analytics, visualization platforms, and so forth. The scope is generally very broad, you know. Okay, this is the EO for Society website. I invite you to take a look, and please do feel free to get in touch with me if you have any ideas or you want to discuss anything for activities that you might be interested in doing. We're always available for providing feedback on ideas, and happy to discuss with you. That's all I had. Thank you.